Right, next up we have Ken Livingstone giving us a seminar on basic introduction to subsea. So over to you, Ken.
Okay, good morning all again. So today we're doing a basic introduction to subsea. Okay. So what we're going to be talking about today is what is subsea, general marine operations, dynamic positioning, subsea construction vessels, mainly regarding subsea cranes, pipelay vessels that is, diving vessels, ROV types, and finish off with questions. Is everyone seeing the screens okay? Okay, moving on. What is subsea? Subsea is a term used for all types of vessels, works, and operations that are designed to facilitate or carry out works below the sea's surface. Subsea is part of offshore, which incorporates both subsea and surface type operations, such as supply boats, PSVs, crew boats, accommodation vessels, helicopter operations, heavy lift vessel liftovers, which are not works that are subsea, they are surface type works. And we're not going to be talking about them today. Oh, sorry. Okay, a basic subsea field arrangement showing flow lines, subsea manifolds, risers, 2 platforms. And that one's a little bit clearer, outlines various different pieces, pipelines, export pipelines, jumper leads, plets, that's pipeline end terminations, subsea manifolds. All of these works are things that are installed using subsea cranes, connecting up with ROV or possibly divers, diving work offshore. Okay. And a subsea connected turret mooring to an FPSO, where the actual FPSO will rotate around that turret. And what you can see there in the yellow is a flow line, and little orange floats to take some of the weight off the pipe. Okay, moving on. General marine operations. What you can see here is one of the Technique vessels. It's a DP3, diving support, heavy construction vessel, the Deep Arctic. So, some specific types of marine operations. You'll have dynamic positioning vessels offshore. You have subsea construction vessels, which use subsea cranes. Pipelay, which are various different types of pipelay. There is rigid, which requires spill bases ashore to run pipe onto the ship. You have rail lay, you have S-lay, you have J-lay, and you have flex-lay. And we'll come on to those a little bit later. Then you have diving, air and saturation diving, and then you have remote operating vehicles. Some other subsea topics, but we're not going to be discussing these today, are seismic vessels and operations, anchor handling and subsea moorings, dredging, and cable laying, although cable lay is, in the operation itself, is very similar to flex lay. Okay, dynamic positioning. Another DP vessel, the DP2 multi-purpose vessel Scandi Hercules. Okay, what is meant by dynamic positioning? From Wikipedia, dynamic positioning, DP, is a computer-controlled system to automatically maintain a vessel's position and heading by using its own propellers and thrusters. The propellers and thrusters control surge, which is a vessel moving in a forward and aft way, sway, vessel moving in the thwart strips, port to starboard mode, and yaw, vessel heading changing from straight ahead to either port or starboard. So this is a little good drawing showing the principles of DP. There are 6 freedoms of vessel movement. There's a DP controlled axis, which is yaw, surge, and sway, as we have just discussed. And then the measured, which are not controlled, which is roll, pitch, and heave. So DP is concerned with the automatic control of surge, sway, and yaw. Surge and sway comprise the position of the vessel, while yaw is the vessel heading. That's a good little example. So if you've got current, the red arrows, current, wind, and waves, which you cannot control, but sway, surge, and yaw you can control by your azimuth thrusters, your tunnel thrusters, and main propellers and rudders. So how does a DP computer control the vessel's position? The vessel location is set and fixed by an onboard DP computer, and any effects or changes in the conditions are measured by a range of reference systems, and sensors, a number of which are used at any one time, depending on prevailing conditions, to send offset signals to the DP computer. Just to go a little bit on that, you have a range of reference systems, but you may not be able to use all the ones that the vessel has. For instance, you may have a taut wire to use as a reference system, but the vessel is working over live pipelines, and in that situation, you wouldn't be able to use the taut wire. You would need to use other types of reference systems. Okay, so when a computer detects an offset, which is a force or an indication that the vessel is moving away from its set position, then the computer sends a signal to the vessel's forward and aft thrusters and propellers to bring the vessel back to the assigned set position. Okay, so this drawing is a basic DP controlling sequence. The vessel location set point is set in the vessel's mathematical model. As the vessel moves due to action of the wind, current, or waves, an offset will be detected by the reference systems and the sensors, which is passed into the original model, where the difference is calculated, and that difference sends a signal to the DP controller, which instructs the thrusters to apply a thrust in opposite direction to which vessel has moved off of its set point. As the vessel moves back into position, the signals from the reference system decrease and reduce the thrust. The controller reduces the thrust until the vessel settles back into its original set location. So different types of reference systems. You have your differential GPS, DGPS, which satellite measures the difference between the moving vessel sensor at a fixed point ashore, and then an offset is sent to the vessel DP computer. This may not be the reference system of choice if there are line of sight obstructions to the satellite. For instance, maybe a tower on a platform close by, which means that your actual signal from the satellite with the ship is just not working. You have microwave systems, examples being the radar scan or a radius, where a microwave beam is sent out from the vessel, a moving vessel, to targets on fixed platforms, and offset is then sent to the vessel DP computer. Will not be of use in any open seas because there's nowhere to fit a target. A target being stepping back, a microwave will use a transponder which is fitted onto the platform to use from the radius. The range is typically 500 to 1,000 meters for a radius. Then you have laser systems, which is a fan beam or a side scan. Works on the same basis as the radius, but uses a small prism, which is a reflector installed in a nearby structure, and there's the same operating restrictions. These are structures nearby to put the prism on. Range is typically up to 2,000 meters. So the difference between the microwave and the laser beam and the sensors is that a microwave will use a transponder on the fixed platform, and a laser will use a reflector. So then you have acoustic DP reference systems, an HBR or a HIPAP. This works on the basis of having a transducer placed in the ship's hull. It's normally lowered below the vessel hull by a pole through a ship side valve or a bottom valve, and one or more transponders placed on the seabed. The transducer sends an acoustic signal to the transponder in the seabed, which is triggered to reply. The velocity of sound through water is known, so the response time is used to calculate the distance. Also, the transducer can determine the angle at which the signal is received. Using both these, distance and angle, the position of the vessel relative to the transponder is known. The disadvantage of this system is that external noise, noise from your propellers, can interfere with the readings because it is using a sound signal. So there are three types of HPR and HIPAP installations used. The ultra or short baseline, USBL or SSBL, which has one transponder and one transducer. Then you have the short baseline array, uses an array of transducers on the ship's hull. On a long baseline, which uses an array of at least 3 transponders. So the SBL uses additional transducers, the LBL uses additional transponders. Then you have the torque wire, which I mentioned briefly a few minutes ago. It's possibly the oldest type of reference system used in DP systems today. It works on a wire being lowered to the seabed with a clump weight on the bottom. The wire passes through a gimbal head, which is basically a ring at the top of the torque wire. So when it's initially set up, the wire passes centrally through the gimbal head, and the wire runout is measured, so you have the length of the wire. As the vessel moves, the changing angle of wire passing through the gimbal head is measured, and by knowing the length of wire run out, the distance moved can be calculated. This system is good for operation in shallower depths, but may not be the reference of system or preference for deeper waters, as a long wire can be affected and curved by currents, giving an incorrect reading. As I mentioned earlier, it's also not suitable if the ship is alongside a platform and you have live pipelines underneath. You don't really want to be dumping clump weights down towards the seabed with the live pipelines underneath you. So then we go to sensors. The previous ones were reference systems. For sensors, you have your gyro or your gyro compass, which is used to determine the vessel's heading. You have wind sensors, which are fed into the DP, known as called feed forward, so that the system can anticipate the wind gusts before the ship is blown off position. And you have motion or vertical reference units, MRU or BRUs, which are used to determine the vessel's roll, pitch, and heave. So the definition of a Class 2 DP vessel, DP2, is that the vessel must maintain an automatic and manual position and heading control under specified maximum environmental conditions, during and following any single fault, excluding loss of a compartment. And it has 2 independent computer systems. This basically means that the vessel is fully redundant, meaning that there are 2 of every system or piece of equipment on board in operation at any time, such that if one piece of equipment goes down, there is a secondary piece of equipment in place to take over, so the vessel will not lose position. So just on that, you also have 2 switchboards with a bus tie breaker, and the general practice is that bus tie is open during DP, so that if you use one side of a switchboard, the other side of the switchboard will still maintain power to half of your systems. Okay, so there are various different types of DP, and depending on the classification society, they reference some system. They reference them differently. For a normal Class 2 DP vessel, ABS will have a reference DPS2. Lloyd's will have it DP in brackets AA, and the DNV will call that DPS2 DIN plus Otter. That's just an example, but the different classes are shown there. Vessel also has ERNs, environmental numbers. It used to be 3, there are now 4. So the ERN is a number which determines the ability of a ship to maintain position when it interacts with the combined forces of wind, current, and waves at the vessel's most sensitive point, typically on the beam. The ERN consists of 4 digits. The first number represents the ability of the vessel to maintain its position on all thrusters. The second number represents minimum effect of single thruster failure. The third number represents the maximum effect of single thruster failure. And the fourth number represents the ability of the vessel to hold its position in the case of the vessel system worst case failure. So the best possible number, ERN number for a vessel, is 4 times 99, 99, 99, 99. So, and this was taken from the DNV rules for classifications of ships. Quite often you'll see an ERN number shown in a vessel spec sheet that the companies hand out, because if they do have it at 99, 99, 99, 99, it means the vessel is very good at holding position, and obviously the operator would want to promote that to potential clients. Okay, moving on. Subsea construction vessels and subsea cranes. So subsea construction vessels have cranes that are fitted on their after decks that can deploy loads subsea, quite commonly to 2,000 to 3,000 meters depth. And in general, the cranes range from 50 tons to 400 tons safe working load. These vessels may also have other systems on board to support offshore construction and subsea services such as ROV and/or saturation diving. There are also offshore construction vessels which are called heavy lift vessels, which carry out projects such as lifting topsides onto installed jackets onto like an offshore rig. But this is not subsea work, so we're not going to discuss that today. Okay, a few examples of vessels with subsea cranes on the aft decks. Okay, so subsea cranes, common characteristics: active heave compensation, normally called AHC. AHC is a technique used to reduce the influence of waves on offshore lifting operations. It's designed to hold a load on a crane motionless, relative to the seabed, counteracting the vessels moving or vessels rolling by the effect of waves. The system normally incorporates a motion reference unit to sense the vessel movements and a control system, normally a PLC, to control the active parts of the system that are to react to counter the wave action. The major benefit of this function is that it ensures the load is motionless at close to seabed when the load is being worked on, and it isn't moving up and down due to the vessel at the surface rolling. So the vessel can be rolling at the top, but the load will be stationary at the seabed, and that's what you want when you're doing maybe a stabbing action or putting something onto like putting in a Christmas tree or something, that you're actually stabbing it in when you're installing it. Or you've got divers trying to connect something with a pipeline, like a pipeline end manifold, and you want to stab them together to bolt them up. You don't really want the load to be rising and falling with the ship rolling with the waves. So most common types of AHC are the electric winch system, where the wave movement is compensated by automatically driving the winch in the opposite direction to the wave motion, and this is a common in ROVs. And there's a hydraulic winch system, which can use either a hydraulic winch or hydraulic cylinders, or a combination of both. Okay, so, and apart from active heave comp, you also have constant tension. Constant tension is used to maintain a constant tension on a load. A line pull is preset prior to lifting operations, and once engaged, the load is measured by a load sensor, and if the value difference from the set point, then the winch will pay out or in to maintain the set load value on the wire. Stops the wire going loose. This differs from AHC, as AHC works to maintain position of load against the wave action with respect to the seabed location, whereas constant tension simply maintains load on the wire regardless of where the load is sited. It keeps the wire taut at all times. Okay, and then we have, for the cranes also, you have load charts, or with your DAF, dynamic application factor. When crane manufacturers design offshore and subsea cranes, they produce crane derating charts. Sorry, should we? On a number of different indicative significant wave heights, which are normally based in the NATO sea states. These charts do not take into account any other safety protective systems such as AHC, CT, etc. So when a ship's in harbour, there's flat calm, the crane would operate at 100% of its safe working load. But in offshore conditions where there are wave effects in the vessel, it's generally assumed that a minimum DAF of 1.3 will be applied, which is basically derating the amount of load you can use on a crane. So if you have lifting 50 ton in harbour, if crane's rated at 50 ton, you would use that as a harbour lift in port. But when you're up at sea, you'll be thinking of 1.3, 50 divided by 1.3, which will bring you down to 30 something. 1.3 is just a general rule of thumb. The DAF can change depending on the load. If the sea states are high, it may be a DAF of 2. A 50-ton crane will then be derated to 25-ton, for example. Basically, because of the waves, you are derating your crane, so the effects of the wave action on that load does not overload the crane. That's why you reduce the load. Okay, those are the NATO sea states that I mentioned. If you look at the middle column there, that shows you the relative Beaufort number, wind speed, and the wave heights. It refers to the NATO sea states. Okay, so load charts continued. So we consider there are no protecting influences such as AHC in place, and the crane manufacturer has to put in place a derating factor to reduce the maximum load that the crane can carry. The value to be derated is maximum load, less loads impacting on the crane when operating in vessel wave-affected conditions. The greater the wave height the vessel is operating in, then the greater the derating value that has to be applied. As I said, you could have a 50-ton crane if it has, and you're working in pretty bad conditions. It could be a DAF of 2, which means you're down to 25 tons. So a quick example of derating. If a 10-ton rated crane has a load of 10 ton and a flat calm plate at 1 metre, it's being lowered below the seabed, and the vessel suddenly rolls so that the crane lifts the load, and a water pressure of 1 ton is exerted in the top of the plate. Then the actual load the crane sees is 11 ton, which would overload the crane. So in this case, the crane would be derated with a DAF to bring the crane load down to 9 ton, and you would have a maximum of 9 ton under those conditions. You would not consider lifting a 10-ton load. So I'm now going to use a couple of examples from a crane manufacturer, and I will apologise because I've actually queried this with the manufacturer. They've said they will revert, and they haven't, because I found a couple of anomalies in these charts. But anyway, you see 2 crane load charts in a second. So in these examples, with the OEM, the crane manufacturer, uses a sea state 2 and sea state 5 in the charts. Shown below. Sea state 2, the conditions, small wavelets all over, no whitecaps, wind speed 4 to 6 knots, which is the wind felt in exposed skin, and leaves will rustle, and a wave height of 20 centimeters. A sea state 5, moderate waves, many whitecaps, wind speed of 17 to 21 knots, and a wave height of 2 meters. Okay. So sea state 2, this is a crane. With a sea state 2, it has a 20 centimeter wave height. This crane manufacturer has given a chart with a derating application factor of 1.4. The sea state 5 is a derating factor of 2. So it reduces the crane's safe working load from 50 tons to 25 tons. Sorry. Okay, moving on. Pipe lay. There are different types of pipe and different methods of lay when installing pipe subsea. The main types and methods are following. There's rigid steel pipe, S-lay for shallow waters, and J-lay for deeper waters. It can also be reel lay for smaller diameter pipe. With the J-lay, the pipe leaves the vessel in almost a vertical orientation, so the only bend in the pipe is when it reaches the seabed. S-lay commonly leaves at the aft end of a ship, almost in a horizontal position, via a stinger. This says it angles closer horizontal. Flexible pipe, reel lay and flex lay. It's normally laid overboard or through a moon pool from vertical reels or horizontal carousels on a ship. Okay, so some examples. The first one at the top is an S-lay vessel, and you see the vessel, the shape of the pipe is almost like an S. The next one down is a J-lay. Again, it comes down almost vertical and then sees the seabed, so it's in the shape of a J. And the bottom is just a reel lay from the ship. Multi-purpose pipelay vessel, has carousels, it's got a crane, because it's going to be lifting reels of pipe or carousels of pipe on and off the vessel. If you look at that, this has actually got two 1.1250 metric ton carousels, so all that has to be lifted, so you need a ship's crane. You have an optional J-lay module with rigid pipe straightening sections in it. It's got the moon pool for the J-lay. Okay, moving on. Global 1201, which is Technique's vessel, heavy lift and S-lay vessel. It has a pipe lay coming out the back. This is a firing line in an S-lay vessel. And this is how it happens below the decks. You have your welding stations as the pipe's moved. You have tensioners to keep the tension on the pipe so it doesn't run away. You have your non-destructive testing area towards just before it goes subsea. And then where the sections have been welded together, you put the fuel joint coating on just before the pipe is sent overboard. So it's basically a factory. You'll have your first, at the very first, your root weld at the front end of a ship, and then subsequent welds as the vessel moves along pipeline. Some photographs of pipes being welded and the tensioners inside an S-lay vessel. Some examples of the stingers with the vessel going off. And if you see the bottom right, you'll see that all these vessels usually have a range of support vessels for them for bringing the sections of pipe to the ship to go on board. So from a surveyor, getting a job with a pipelay vessel, you can have all sorts of vessels to support you. You can have crew boats, pipelay pipe supply boats, lots of vessels that require rovers or seamen, or even on-off hire condition surveys. There's a fair bit of surveyor work involved in these operations. This is a rigid reel lay vessel where the pipe is actually, it's not an S-lay, there's no welding. The pipe is actually welded ashore, and then it's reeled onto that big reel in the center of the ship. And then when it comes off the ship, it goes down through the ramp at the back, which has straightening sections to straighten the ship before it goes straighten the pipe before it goes subsea. There's a reel lay system for welding to a vessel deck. As I say, the ships will have pretty big cranes because they'll be lifting these on board and fixing them onto the deck. Give you an idea of the size of a carousel for horizontal lay. Okay, so that's it for pipe lay. Moving on to diving. There's a DP2 diving support vessel. The name has actually changed. It's now just the Nusantara. It's no longer the Mermaid Nusantara. Used to be called the Windermere. Okay, so the saturation diving layout. You'll have an SPHL, which is a self-propelled hyperbaric lifeboat in case the vessel the ship sinks. You have your diver decompression chambers. I have your TUP, which is transfer under pressure, moving between changes to the bell or moving between chambers to the lifeboat. A couple of photographs. The one on the left shows you the bunks of the divers living inside their chamber. The one on the right shows inside the bell. The exit and the entry is through a horizontal door seen at the back of that photo. And when the bell is working at depth, the exit and entry is through the bottom bell working moon pool door. So the two doors. You can actually see the door open at the bottom of that photograph on the right. And as I say, straight in the center of it, you see the door, horizontal door that goes to and from the chambers. These photographs were taken at a training school. These are not actually working photographs. Some diving work subsea. The bell's at the working depth. The divers have come out through the bottom door and they're shown standing on the clump weight. The clump weight goes down with the wires. It goes down with the guide wires. Guide wires go through the bell structure. You can actually see the wires on the left. And then the bell goes up and down those wires to the clump weight, to the seabed. So a couple of diver works, cleaning marine growth of a subsea structure, carrying out subsea welding. Quite often they'll be doing subsea bolt tensioning as well with hydraulic bolting systems. There's all sorts of things divers can do. So what is saturation diving? When a diver dives below the water surface, pressure in the body increases and the nitrogen in the air breathed in starts to give a narcotic effect. The greater the pressure at the depth, the greater this narcotic effect. So this increase in pressure also causes an excess of oxygen to be absorbed into body tissues, which can cause a variety of symptoms, including damage to body cell membranes, collapse of the alveoli in the lungs, retinal detachment, and seizures known as hyperoxia. The depth when diving at which the pressure in your body starts to give these effects is around about 30 meters. Therefore, commercial air diving is generally carried out above 30 meters, and at 30 meters and below, saturation diving is employed. So in recreational diving, 40 meters depth is considered the maximum for diving using air. Although there is a possibility of effect at this depth, it's a symptom recognised by experienced recreational divers who simply come up from that deeper depths, they start to feel the effects coming on. These effects are dispelled quite quickly once the pressure in the body eases at 40 meters. So, in air diving, normal air is used, which is basically 79% nitrogen and 21% oxygen. In saturation diving, helium is introduced into the diving mix, replacing the nitrogen and also reducing the oxygen content. This mix is known as heliox, which is a mixture of helium and oxygen. It is generally believed that helium and possibly neon are the only gases that do not have a narcotic effect when breathed under pressure. So basically the helium is replacing the nitrogen, which does give that effect. So oxygen is still required for breathing. However, the greater the diving depth and the pressure, the less oxygen the body requires. And the helium and oxygen, heliox percentage mix is amended accordingly. So for saturation diving, known as generally sat diving, divers live in pressurized chambers on board a ship, and they're blown down, pressurized, to the working depth at which they will be working. So if they're going to be working at, say, 100 meters and breathing a mixture of helium and oxygen, when they come up from the dive, they will be under that same pressure into the chambers. That chamber will be pressurized to the same pressure that they would be doing at the working depth, and they will still be breathing the same heliox mixture as they would be at that working depth. Okay, so again, an example, diving teams working at seabed 200 meters. The living chambers on the surface will be pressurized to whatever the pressure is at 200 meters water depth with the same mixture of heliox that divers working at the seabed are breathing, as I just explained. Divers generally live inside these confined spaces, these chambers, with other divers in close proximity for a 28-day tour of duty, 1 month. Decompression time, to slowly bring the body pressure back to the surface pressure and breathing normal air, generally takes 3 to 4 days to bring it back slowly to ensure there's no bend sickness. Okay, a little separate one is your diving umbilicals. When a diver's coming out the bell, you need to control the diver's umbilical length. There should never be a sufficient umbilical on the diver that it can be reached back up to the surface and drawn into the vessel's propellers. And you have charts. Every diving ship will have a chart showing the umbilical length required from the bell for the safe working distance away from the thrusters, away from the closest thruster, I should say. Okay, moving on, ROVs. ROVs are remote operated underwater vehicle. An ROV is a tethered underwater mobile device. They are unoccupied, highly maneuverable, and operated by a crew on board a vessel. That's from Wikipedia. Mainly used to carry out subsea works using hydraulically or electrically operated tools, and they have cameras to carry out visual seabed inspections and surveys, and are alternative to using divers or other works required subsea. An ROV is generally used in preference to divers when work is required in dangerous locations or situations where you don't want to put divers into harm's way, or work is required at depths greater than divers can operate. Some examples of ROVs. Some more examples. Some ROV support vessels. You generally see the LARS, which is LARS is for operating the ROVs, launch and recovery systems. Okay, that's it. Any questions? Thank you.
Yes, if anyone's got any questions for Ken, we're here to answer them now. We've got some time. Yeah, it doesn't look like anyone's got any questions, Ken, at the moment. So thank you very much for a great presentation there.
Good. All right, thank you. We've all gone to sleep.
Yes, we'll be back at 3 o'clock with a presentation by Gary Lowell. So until then, thank you very much.
Okay, thanks everyone.